In the previous video, we have learned how to achieve a simple linear regression model. In this video, we discuss how to evaluate the quality of a simple linear regression model. Depending on the purpose of the linear regression, our focus on the regression outcome will be different. In explanatory analytics, our goal is to explain relationship between the predictors, explanatory variables, and the target. So we care more about the goodness of fit of the model, and each variable's explanatory power is important. In this sense, R squared to be introduced in this video is important. Meanwhile, parsimony of models normally enables better interpretation, which is even more meaningful in multiple regression to be learned in other courses. In predictive analytics, our goal is to predict target values in new data where we have only the predictor values. So we want to reduce the prediction error, such as the standard error of estimate, which is to be introduced in this video as well. To measure the quality of regression, we hereby introduce three variation concepts. The first one is the sum of square total, denoted by SST. It's the square differences between the observed dependent variables and its mean. You can think of this as the dispersion of the observed variables around the mean, much like the variance in descriptive analytics. The second term is the sum of squares due to regression, or SSR. It is the sum of the difference between the predicted value and the mean of the dependent variable. Think of it as a measure that describes how well our lines fit the data. If this value of SSR is equal to the sum of squares total, it means our regression model captures all the observed variability and it's perfect. The last term is the sum of the squares error, or SSE. The error is the difference between the observed value and the predicted value. We have talked about this in the previous video on least square error approach. Note that people also use this notation, SST, SSR, and SSE, for different concepts outside this course. Please do not confuse this concept with those that are not in this course. Statistically, we have SST equal to SSR plus SSE. The rationale is the following. The total variability of the data set, SST, is equal to the variability explained by the regression line, SSR, plus the unexplained variability known as error, SSE. As we previously discussed, the least square error approach used in obtaining the best linear regression model is based on minimizing SSE, the error sum of squares. The smaller the error, the better the estimation power of the regression. For your information, here are the equations to compute SST, SSR, and SSE in more details. Although we do not require computing these equations by hand in this course, it is useful to understand these important concepts in more details. In specific, the total variation is given by SST equals summation from I equal to 1 to n of parenthesis y sub I minus y bar parenthesis squared, which is also equal to summation from I equal to 1 to n of y sub I squared minus parenthesis summation I equal to 1 to n of y sub I parenthesis squared over n. SSR is equal to the summation from I equal to 1 to n of parenthesis y sub I hat minus y bar parenthesis squared, which is also equal to b sub 0 times summation I equal to 1 to n of y sub I plus b sub 1 times summation from I equal to 1 to n of x sub I times y sub I minus parenthesis summation I equal to 1 to n of y sub I parenthesis squared over n. Again, SSR is also referred to as the explained variation. And SSE is equal to summation from I equal to 1 to n of parenthesis y sub I minus y sub I hat parenthesis squared, which is also equal to summation from I equal to 1 to n of y sub I squared minus b sub 0 times summation from I equal to 1 to n of y sub I minus b sub 1 times summation from I equal to 1 to n of x sub I times y sub I. Note that SSE is also referred to as the unexplained variation. In the output of the Excel data analysis regression, we can find the values of SST, SSR, and SSE in the ANOVA table. ANOVA table is also called analysis of variance. This table is exactly the same we pointed out in the previous video. In the first row, the DF means the degrees of freedom. SS means sum of squares. MS means mean square error equal to the regression SS over regression degrees of freedom and residual SS over residual degrees of freedom, respectively. F is the overall F test for the null hypothesis to be discussed in the next video. Note that T test is for each individual variables, but F test is for the overall model, which is preferred if we look for the goodness of fit for the entire model. Significance F is the significance associated p-value for the F test. The intersection between the regression in the first row of the data here and the SS is the value of SSR, which has a degree of freedom of 1. The intersection between the residual row and the SS is the value of SSE, whose degrees of freedom is equal to n minus 2 equal to 8 in this specific case for the house price case, where n is the sample size equal to 10 in this case. The intersection of total row and the SS column is the value of SST with the degrees of freedom n minus 1 equal to 9 in this specific case. You can verify that SST is equal to SSR plus SSE. We now define one very useful statistic to measure the quality of the regression model. That is the coefficient of determination, which has been usually denoted as R squared. R squared represents the proportion of the variance for dependent variable that is explained by an independent variable or variables in the regression model. Mathematically, R squared is equal to SSR over SST, which is also equal to regression sum of squares over total sum of squares. R squares measure the strength of the relationship between our linear regression model and the dependent variables on a convenient of 0 to 100% scale. 0 represents a model that does not explain any of the variations in the response variable around its mean. 100 represents a model that explains all the variations in the response variable around its mean. Usually, the larger the R square, the better the regression model fits your observations. However, this guideline has important caveats. A high R square is necessary for precise prediction, but it is not sufficient by itself. We will take other concepts such as standard error and F-test into our consideration later. Meanwhile, we must verify that all assumptions required by regression models have been all satisfied. Because further discussion of these assumptions is beyond the scope of this course, we will skip them here. Here we further show several cases of potential R squared. The leftmost graphs represent perfect linear relationship between X and Y. That is, 100% of the variation in Y is explained by variation in X. However, this perfect situation does not happen in practice. The rightmost graph suggests no linear relationship between X and Y. That is, the value of Y does not depend on X. So the R square equals 0. Most of the R square happen in a way similar to the middle graphs, in which some but not all of the variation in Y is explained by variations in X in the linear regression model. We now look at the output of Excel data analysis regression. We have discussed the bottom two tables previously. The middle one is about ANOVA, and the bottom one includes the coefficient information of the regression model and the t-test to be discussed later. Hereby, we further explain the meaning of this regression statistics list in the top table. First, multiple R is the correlation coefficient. It tells you how strong the linear relationship is. For example, a value of 1 means a perfect positive relationship, and a value of 0 means no relationship at all. Actually, it is the square root of R squared. Second, the R square is the coefficient of determination that we have just discussed. For example, 58% means the 50% of the variation of Y values around the mean are explained by the X values. In other words, 58% of the values fit the model. Third, adjusted R square is adjusted based on the R square and the numbers of variables in a model. We want to use this instead of the about R squared if you have more than one X variables in multiple regression, which is not covered in this course. So adjust R squared is very useful in multiple regression. Fourth, standard error of the regression is an estimate of the standard deviation of the error. This is not the same as the standard error in descriptive statistics. The standard error of the regression is the precision that the regression coefficient is measured. If the coefficient is large compared to the standard error, then the coefficient is probably different from 0. Fifth, the observations represent the sample size or the number of observations in the sample. Mathematically, based on the SSR and SST values provided in the middle ANOVA table, we can also compute for the R squared value as follows. R squared equals SSR over SST equal to 18,934 over 32,600, which is equal to 0.58. Therefore, in the practice quiz, you may compute the R squared using only SSR and SST values, even you don't have the R squared value over here. And then you can use this equation to figure out the R squared value. Perfect prediction is practically impossible in almost all disciplines, including economics and business. So from the perspective of predictive analytics, how can we tell whether a regression equation is a good predictor? To the end, we need a measure that will tell how inaccurate the estimate might be. A standard error of estimate is such a choice. The standard error of estimate is the measure of variation of an observation made around the computed regression line. Simply, it is used to check the accuracy of prediction made with the regression line. Mathematically, standard error of the estimate is given by S sub yx equal to square root of SSE over n minus 2 equal to square root of summation from I equal to 1 to n of parentheses y sub I minus y sub I hat parentheses squared over n minus 2. Well, SSE is the error sum of squares, and n is the sample size. When you have two or more comparison models for the same dependent variables, the smaller the standard error of estimate, the better prediction is the model. We can also find the value of standard error of estimate from the first table, which is represented by the standard error. In this specific case, the standard error of estimate is equal to 41.3. As we can see from these two graphs, the first one has a smaller standard error of estimate, and the second value is larger. Meanwhile, it is also recommended that we should judge on the standard error of estimate relative to the size of the dependent variables. For example, in the house pricing regression model, a standard error of estimate equals to $41.33K is relatively small compared to the house price in the range of $200K to $400K. In summary, this video has discussed the difference between explanatory analytics and predictive analytics and suggests some statistics for different analytics purposes. In particular, we introduced 3 different sum of squares in SST, SSR, and SSE. We emphasize the importance of R squared in exploratory analytics and standard error of estimate in predictive analytics.